That's essentially everything that is said here on this slide. And if you want to look at details, then here are the files. All right, and now this is the obvious translation of the informal description of what receive does, isn't it? So let me just point out a little bit. So it's again the typical form of VST specs. You have seen them now about 20 times. Precondition, postcondition in their prop local sept form. What do we have? Well, we have now these two separation logic predicates. This is our interaction tree of the externally visible events. This is the state of all the sockets, the socket map that I was just mentioning, always in blue. So we start with a particular situation of that part of the world and a particular interaction of the world. We have again some logical specifications that tell us something about the trace inclusion here of what we actually want to do, namely a receive operation with these client connections of those many bytes, and then whatever we get as a return value, we want to shove into K, and that's included in the behavior of T. Which is universally quantified up there, and so is the continuation and the socket map, blue. And then when that call returns, we will have some result value. We will have an updated, possibly updated socket map. We have a component R, and we have a content. R is the actual return value that tells us how many bytes were actually received, and we can check that, and depending on the return value, actually either the receive was successful or it wasn't. So there's a couple of logical reasoning here, and also in the post condition we have the updated socket map and the appropriately advanced tree. Again, that depends a little bit on what the result value was, and also we have, of course, in our data buffer, that was the third component here of the right length, of alloc length. We have now contents in here, where previously we just had data at. So that is the maps to underscore predicate in the correct type form that you know from separation logic. And the detailed specification, whether this is still uninitialized or maybe just half of the bytes have been filled or whatever, that's all specified in this propositional case. So with that explanation, maybe that looks slightly less scary, but it's still quite some work, A, to get it intuitively right, and B, show that it actually allows us to push some programs through. So that's what particular Nicholas has been doing for the last half year or so. And not only for this instruction, this specification. Right, indeed, the one for send is similar and similarly complex. And the specs for bind and socket that I haven't shown will then just be about the SOC API. And again, these axioms in the end will need to be connected to what Serdikos thinks about these operations. Okay, then we write some C program, and maybe I don't show you the file. There's the link. It has 630 lines of C code currently. Great. So it does this swapping where you always get the previous value back, which may actually have been put there by a different connection. So let's write an informal spec, right? Well, this is what we actually have. This is a C program that comes again at least with an informal spec. It takes 8 lines. So this is what this description says. It's helpful, but not quite a spec that we can start with in VST again. So, as you will remember from several talks now, we layer the verification of this again in several steps. That wasn't quite so necessary for the character I/O, but it helps really here. So we first define a model in Galena that replicates a lot of the information that the C program has before linking it as a refinement to the more abstract trees. So in particular here in this C-like specification, we say sort of we replicate some of the structs that you see in the C program to allow more abstract reasoning about that. So the similar data structures are used and to some extent also similar control flow structure. And so these are just COG definitions together with appropriate update operations, and so and of course the point of that is then that we can make definitions of these sort of low-level interaction trees for functions for operations such as reading from a connection that is informally specified here and directly has a counterpart in the C program. So that's why one of the functions in the C code actually. And yeah, it's one of our I trees with this instantiation of the events and that return type, if you remember the structure of these trees again. Okay. You may observe that this is actually slightly longer than the C code, but at least it's in a more structured language, Galena, so that's probably still a reduction in complexity. And again, similarly for all the other data structures and functions in the C code. So this is in particular then the VST specification that comes out of this for the con-read function, and it is roughly as complex as the one that we just saw, maybe slightly less fine prints, but again, roughly we move a socket API and an I tree forward in a certain sense, and we can say sort of how the connections have been updated and what other structures have been modified in the memory here. All right, and then we grind again. This proof is 430 lines in the current version, so more VST proofs. Great. Potential for more automation. And we do that with all 16 or so functions. And in the end, you can verify something like this. This all functions correct, which again combines the proofs of the individual functions to a statement about the entire program, guaranteeing that if there were any sort of mutually recursive calls, for example, between C functions, all that would be resolved correctly. And then this is something that we want to now combine with the top-level property that Benjamin mentioned in his talk. So we make a definition that our swap server is overall correct if there exists an interaction tree of this more C-like, slightly more lower level kind, called red tree there, which A specifies the behavior of the C program, and that's what the first conjunct says, and it should also be a refinement of the more abstract swap server that specifies the network visible interaction between the program and its environment. And in particular, this notion of refinement includes this network scrambling of messages that Benjamin outlined, which roughly corresponds to something like the linearizability that Zach discussed this morning. And we currently have a couple of simplifications because we don't, for example, support yet shutdown. So this is again a little bit of work on our to-do list. And yes, there are still one or two smaller admits in the outer parts of these proofs, but all the 16 core functions of the C program actually have been pushed through.
That red tree is the precondition for main?
Yes. It's the precondition for main, so it tells you that it is sort of an upper bound on what the tree will do. Sort of it gives the program all permissions it needs to step through the program. Of course, there's no guarantee that the program will do all the options present, because we're in a partial correctness logic and doing safety properties here. All right, so let's step back a little bit. This is one way, or the first step in sort of lowering the observer visible behavior of a program to something that we can reason about in C. And that gets us a little bit further down in our entire chain of systems. Let's briefly abbreviate this property with program satisfies the swap observer, or similar statements in a second. So what do we need to do in the next 2 years or so? Now clearly the swap observer doesn't have quite the features that we expect from an actual web server, no matter whether it's in a router or actually connected to user interactions. So clearly we need to scale things to bigger programs and bigger proofs and bigger specs. And actually understanding the specifications of HTTP is a challenge in itself, and needs to be validated by a lot of actual testing of Apache and some systems like that, and of course then also of our implementation. And that's a lot of the work that Benjamin's team at Penn is doing, using QuickChIC and other techniques. But of course also we want to refine our proof further. So when I introduce this abbreviation, now really of course what we mean is that in the end the C program plus the operating system will have that external behavior. We had this C-like tree as an intermediate stage with this scrambling that connects these two kinds of trees. And if we refine now the system view a little bit more, then this is how that looks like. So we have our C program. These are the yellow network visible actions that I focused mostly about, but I already mentioned that there are also these SOC API instructions or calls to the OS that are not passed on to the outside world. So this is a slightly better view of what actually happens. And if you paid attention, then you'll remember that in the end we really want to compile one with COMCERT. Well, this also with COMCERT, but it has this 30-cost refinement notion that John briefly mentioned in his talk, although it's also based in COMCERT, so it's not unlikely that we'll be able to understand interactions at that level better, and ideally all that will be for the RISC instruction set architecture, which will then be translated or feed into this CAMI refinement sort of CCS process algebra based that Adam discussed earlier this week. Then again, you probably have in the end some interactions with components like the NIC. All of that running in RTL, and hopefully interacting in more or less the same way as we had on the previous page with the external internet. Yep.
Is the CAMI team going to be verifying the NIC?
I don't know actually. And as I mentioned, sort of how other components like the TCP stack or security library or so are in there. So if they might be other programs, and so this should be suitably refined to reflect the structuring of the hypervisor and other programs that might be there. But this is at least one way to illustrate what we hope to have in a couple of years' time or so. All right, so the challenge then is obviously to understand and make sure that all these various notions of refinement actually amount to something that makes sense from top to bottom. Keep your fingers crossed. Or phrased in a different way, that's the real challenge, to have something where we can fill in these dots there. All right, so I hope this has given you a little bit more of an idea how we in principle can use something like these interaction trees to specify interacting systems at many levels of interactions. In particular, we've more or less bridged this gap from the abstract Gallina interaction way with VST. Indeed, structures that are quite similar to the interaction trees were also introduced and found by Zhong in his group over the last 2 years, and Adam. So when we and Steve Steinsvik from Penn in particular started discussing about these things, they raised their hand and said, hey, this looks actually similar to what we've been working on internally in our systems. So that gives us hope that we can actually bridge all these gaps. And in the end, you will feed in some C code and link things top to bottom to Kami, and you can, at the top level in particular, do verification of your top level properties, or you can use tools like QuickCheck before you actually do verification. All right, and with that, I'd like to thank you all for coming to this school. Thank you for lecturing, those of the lecturers who are still here, and the others may see that on the video, I don't know. Thank you to the student helpers and people operating the video camera, for example, for organizing all the student sessions, for participating in the student sessions, and for all the other things you've helped with, and for participating actively in the school and giving us all your feedback. There's actually one thing more that we'd like you to do. I hope over the weekend to put together a little questionnaire where you can give us a little bit more structured feedback. That's also helpful for documenting to the NSF and other outside people what we've been doing, and then we've been actually spending all this money in a reasonable way. And of course, thank you also to the NSF for funding all this effort. Without those big research grants, little of this would be possible. So thank you very much.